So today we will talk about work and energy, and specifically we will talk about a couple of important principles. One is called the work-energy theorem, and a special case of that, which is called essentially conservation of energy. And the important terms that we will look at are work. Well, let me say work and energy here. The important terms are work, by which we mean mechanical work of a force, as opposed to chemical or nuclear or whatever other kind of work one can imagine. And then we will talk about energy, and we'll talk about two kinds of energy. We again talk about mechanical energy as opposed to chemical energy or electrical energy or nuclear energy. And of course, we broadly classify, for the purposes of this course, into kinetic energy and potential energy. And we will see what these terms mean. These, in some sense, are terms of convenience. And of course, potential energy could be gravitational, elastic, and perhaps other stuff. Okay, so this is just meant to be a preview. You're not meant to necessarily know all these terms already. Of course, you're familiar with them, but we will look at these terms in a more rigorous manner in a minute. And then another term is power, which is basically d work by dt is what power is. And by power, we are generally referring to mechanical power, but this definition is certainly generally true. Okay, so again, this is just meant to be a preview, not actual discussion. So these are the important terms. In this area. Okay. Okay, so now let's look at actually an example to motivate some of these terms before actually carefully defining them. Example, if you will. Let's consider a mass on a table, and you have a force F on it. This is sum of all external forces. On this object, and let's say we are defining x from some wall here, some fixed position on the earth. And of course, for the system, we have F equals ma, or F equals mx double dot, which is a, or F equals m dv by dt, where v is velocity, x dot. Okay, so we have F equals m dv by dt. We can rearrange this equation, which has F, well, we can integrate this equation both sides, but that's sort of not what we want to do here, it turns out. We try the following trick. We multiply both sides by v, mv dv by dt, and then try to integrate both sides, basically. So, and then we say fv dt equals mv dv, and then integrate both sides. Okay. Well, fv dt could be written also as f dx, and this could go from, say, the initial position to final position. And integral mv dt is, of course, what is that equal to? It's m, well, integral v dv, which is m from v naught to vf, mv square v naught to vf, v initial to v final, by 2, and that's what we have, half m v final square minus half m v initial square. Okay. Of course, f dv being equal to f dx is basically just, this is just integral x naught to xf. F dv is dx by dt, and then you have times dt, and you can imagine sort of canceling these dt's to get f dx. Okay. So what do we have here? So let me just write the summary statement here. Integral x naught to xf f dx equals half m v final square minus half m v initial square. Okay. Of course, on this side we also have, this is equal to integral f v d t. Okay, from initial position to final position, let's say, whatever the limits may be there. So this equation, what is the significance of this equation? We basically start from f equals ma here, multiplied both sides by velocity, integrated both sides, did a little bit of reduce the integral on the right hand side a little bit, and we got this expression. So it's in some sense, at least in this context, a consequence of f equals ma in this equation. We've derived it from f equals ma, and then what people did essentially is termed this quantity, so define this quantity as work done by force F, so define, and then we define this quantity as change in kinetic energy, where we define the kinetic energy of a particle of the particle, in this particular case, as basically half m v square, so that this quantity is basically final kinetic energy minus initial kinetic energy. Okay. Any questions? So in a sense, you can think of, okay, there is no such thing as work, but we start from f equals ma, and we did a couple of integrals, and we want some words to describe what's going on in this equation, and we just define this quantity, integral of force over the distance traveled in some sense, as the work done by the force, and then we call the right hand side as a change in some quantity, final minus initial, and we're calling that quantity kinetic energy of the particle. Okay, so that's sort of the origins of this principle, and this basically is called work energy theorem. So this thing, one, so equation number 1 is called the work energy theorem, which says work done by all forces, all external forces on an FBD equals change in total change in KE of all objects in the FPD. Okay. So even though we sort of derived this equation in one dimension with this very simple context of the mass going in 1D and you have a simple force and so on, it turns out that this principle called the work energy theorem is generally true in 2D, in 3D, and it's true whether you have a single object or a single particle, or if you have a more complicated free body diagram with multiple particles, etc. So you can have many objects, and the total work done by all the external forces on a free body diagram, on a system of particles, is equal to the total change in kinetic energy of all the objects in the free body diagram. So that's called the work energy principle. Okay. So we will use that. So let me make a couple of more definitions. So equation number 1 can also be written in this manner: integral FV dt. So basically, let's go back up. From 1, we see work equals integral f dx. It's also integral fv dt. Okay. And this quantity is basically called power or mechanical power. Okay. And basically that's because, well, you can imagine work is basically, if you think of work as being the integral of some quantity, well, because the derivative is the opposite of an integral, whatever must go in here is basically dw by dt. Okay. So power is basically d work by dt, and then when you integrate d work by dt, you get work. Okay. So this is the definition. This is again a definition. So I don't mean to say this is the ratio of that thing, but so we define power as that quantity. Okay. So we've defined work. We've defined power, which is what you integrate with respect to time. We've defined kinetic energy. We've defined all these things in 1D. In 2D/3D, work is defined in this manner: mechanical work is defined as integral f dot v dt. Okay. Sometimes it can be written as f dot dx. Okay, where again this is power. When I say this, I mean whatever is inside the integral. Okay, maybe I can make that clear by well, let me just say power equals f dot v here, and that's equal to work. So that's mechanical work in 2D or 3D, where the force is a vector, the velocity is a vector, and you take the dot product here. Okay, so that's the dot product. And mechanical work is still a scalar quantity. So all these are scalar quantities, it turns out. Even in 2D or 3D, kinetic energy will be a scalar quantity, work done is a scalar quantity, power is a scalar quantity. So this is a scalar equation. Okay, we go from F equals ma, which is a vector equation, and then convert it into a scalar equation. So that's mechanical work. Let's look at kinetic energy in 2D or 3D. Kinetic energy of a particle in 2D or 3D is basically defined as half m, basically absolute value of v square or magnitude of v square. So that's how it's defined in 2D or 3D. If you have a vector v, for a particle, we basically have half mv square, where v is the magnitude of the velocity. Okay, so you can imagine it's equal to half m if you're using Cartesian coordinates, vx square plus vy square plus vz square, or in 2D, you can imagine half m vx square plus vy square, or half m vr square plus v theta square, or half m vt square plus vn square. Okay, so all those things are true. Okay, so let me give a big caveat. A sort of a common error that people do is to assume that mechanical work is force times distance. That is not true. Mechanical work is not force times displacement. It is the integral of the force dotted with the sort of differential displacement. If the force is a constant, so if the force is a constant, okay, so in that very special case, work equals integral f dx from x naught to xf, and then you can take f out, so you have integral dx. Because it's a constant, f is a constant, we can take f out, and you basically get f of xf minus x naught. Okay, but this is true only if so this is what we mean by force times displacement. Okay, this is only true if f constant. Okay, not in general true. Not true in general. Okay, so you want to remember that. In 2D or 3D, if f is constant, then work is going to be equal to, it turns out, f dotted with basically r final, the position vector final, minus the position vector initial, r naught or r initial, or whatever you want to call it. Okay, okay, any questions so far? So I'm going to change the notation ever so slightly here. Instead of saying x naught, v naught, and so on, I'm just going to say x initial, I for initial. Okay, I'm just going to put that I, make that I there. Everything else is fine. And I'm going to make this I. Any questions so far? So this is true if force F is a constant. Okay, And recall again, we have this thing called the work energy theorem, where we say work done by all the external forces on a free body diagram equals total change in kinetic energy of all the objects in the free body diagram. Here we've just done one particle, but it's also true for all, like if you have multiple particles. Although in this course, we'll probably just mainly, well, actually we might use multiple particles. Apply work energy theorem for multiple particles. It's important to again realize that this is a scalar principle, and this is the total work, and this is the total change in kinetic energy of all the particles in the system. You don't do component wise or anything like that. You don't try to write this equation for x direction, y direction separately. You just have to sum all the forces in all directions and all the kinetic energy in all directions. That's the only way this equation works. That's super important, okay? This is not a vector equation. It's a scalar equation that has to do with, in some sense, the total work and the total change in kinetic energy. You cannot do components. It's not like F equals ma. Okay, so that's the end of this video. We'll do some examples and further stuff in the next video.